So hello students, this is our the second class on electromagnetic theory. In the first class we discussed about all four Maxwell equations. We have wrote them in both integral form and differential form, and in this today's class we are going to find the electromagnetic wave equation from Maxwell equation. Okay, and I am going to teach you the properties of electromagnetic wave. Okay, so now let's get started. So from one of the Maxwell equation, what we have got del cross E equals to minus del T of B. Okay, so let's say this is the equation number one. So on taking curl on both sides, in this equation what we will get that del cross E equals to del cross minus del V del T. Okay, so this is one of the identity. So what we can write, del cross E equals to del dot E minus del square E. Okay, again the space and time are here independent. So what I can write, I can take this nebula inside this del T. Okay, so I am taking this inside. Okay, so I can write down it as like this. Okay, so if okay, if the space is charge free, then that means okay, del dot E equals to what, rho by epsilon naught. Okay, so if the space is charge free, that is q equals to 0, then obviously rho will also be equals to 0, right? So if rho is equals to 0, then what, del dot E will be equals to 0, right? So del dot E will be equals to 0 for charge free space. Okay, I have written this here. Okay, and again now from Maxwell equation, what we have got, del cross B equals to mu naught J plus mu naught epsilon naught del E del T, right? Where J is what, current density. And for vacuum and dielectric, what I can write, J equals to 0, that means current density is 0. Okay, so in this case what I can write, del cross B equals to mu naught epsilon naught del E del T. Okay, so del cross B equals to what, okay, so del cross B equals to mu naught epsilon naught del E del T. Since J equals to 0, we are removing this term. Okay, so putting these and these, okay, this equation and this equation in this equation. Okay, in this equation what we get, del dot E equals to 0 obviously, so this term will be removed, only this term will be there. So I have written this term here, and del cross B equals to what, mu naught epsilon naught del E del T. Okay, so what I can write, okay, let me explain it here. I have written in shortcut there. Okay, so minus del T of del cross B. Okay, del cross B equals to what, mu naught epsilon naught del E del T, right? But mu naught epsilon naught are constant, so what I can write, minus, okay, this will be an equal sign, minus what, mu naught epsilon naught. Okay, I can written it down as this. Okay, so what I have written here, this equation, let's say this is the equation number 2. So equation 2 can be written as like this. Okay, minus del square E equals to mu naught epsilon naught del square del T square of what, E. Okay, and this minus and minus will be get cancelled. So what we have there, we have this equation. Okay, so this is what, this is electromagnetic wave equation in terms of what, in terms of electric field. Okay, so if we are going to, okay, in electromagnetic wave, what there, okay, there are two field. Okay, one is electric field and one is magnetic field, where electric field and magnetic field are perpendicular. Okay, I am going to teach you in a broad manner. I am going to teach you this in a broad manner later. Okay, in this video. But first of all, let's say, just you assume that there are two oscillating field. Okay, one is magnetic field, let's say B, and one is electric field. Okay, so the electromagnetic wave equation can be written in both in the both electric field and in terms of magnetic field also. Okay, so if I am going to write this in terms of electric field, then this will look like this. Okay, electromagnetic wave equation will be look like this. But if I want to write the electromagnetic wave equation in terms of what, in terms of magnetic field, then how this will look like. Okay, so let's proceed further. Okay, so to write the electromagnetic wave equation in terms of electric field, what I am going to do, I am going to take the Maxwell equation of this Maxwell equation. Okay, del cross B equals to what? Del cross B equals to mu naught J, mu naught epsilon naught del E del T. Okay, and similar concept. Okay, in vacuum on dielectric, J can be treated as 0, J can be taken as 0. So what this equation will be look like? This equation will look like this. Okay, so del cross B equals to mu naught epsilon naught del E del T. Okay, again, if I am going to take the curl on both sides of this equation. Okay, okay, let me erase this. Okay, now if I am going to take curl on both sides of this equation, okay, of this equation, that what we will get? Del cross B equals to mu naught epsilon naught. Okay, del cross C. Okay, how I have written this? Okay, let me explain this here. So on taking curl, what we will get? Del cross mu naught epsilon naught del E del T. Okay, but since mu naught and epsilon naught are constant, so I can take this out of the curl. Okay, so now what I can write? Mu naught epsilon naught del cross. Okay, there will be a cross sign del E del T. Okay, again the same argument, space and time are here independent, so I can take this curl inside this differentiation. Okay, so partial differentiation, so I am taking this inside here, so this will look like this. Okay, so I have written it down directly. Okay, so what we will get now? Okay, so del cross B, using the same identity, what we will get? Del cross B equals to del of del B minus del square B. Okay, again, what is del cross E? Okay, from Maxwell equation, what we have got? We have got del cross E equals to minus del B del T. So I am replacing del cross E by minus del B del T here. Okay, so now what I have got? Again, del dot B, from Maxwell equation, del dot B equals to 0, right? Del dot B equals to 0. So this term will be equals to 0. So this term will be removed and only this term will be remain. Okay, remain in the equation. So this will be look like minus del square B equals to minus mu naught epsilon naught del square B del T square. Okay, so this, again, this minus and minus will be got cancelled. So what we have got? We have got my del square B equals to mu naught epsilon naught del B del del square B del T square, right? So as you can see, these two equations are similar. Okay, so in terms of electric field, what we have got? We have got this equation. Okay, so if we just replace the E by B, that is magnetic field, then what we will get? We will get the electromagnetic wave equation in terms of magnetic field, right? So these are the two equation. Okay, electromagnetic wave equation in terms of both electric field and magnetic field. If you are asked to derive the electromagnetic wave equation from Maxwell equation, you can just write down any one of them. Okay, but if they mention specifically in terms of magnetic field or in terms of electric field, then you have to write the corresponding. Okay, so now let us proceed further. Now what I am going to do, I am going to show you that this, what is the dimension of mu naught epsilon naught. Okay, so specifically 1 by mu naught epsilon naught, it has the dimension of velocity square. Okay, velocity square. Okay, so I am going to show you that. Okay, so as you know what del square is. Okay, so first of all, let me write it down. Del square is what? Okay, del square equals to del x square plus del y square plus del g square. Okay, so as you can see, this is what in 3D. Okay, this is in 3D. But in 1D, what I can neglect? I can neglect these two terms. Okay, so del square can be written as 1 by del x square. Okay, so as you can see, what is the dimension of del square? So if del square is 1 by 1 by del square del x square, then dimension of del square will be what? 1 by l square. Okay, so 1 by l square. So I can write L to the power minus 2. So here I have written this. Okay, again, what from this equation I am going to now find a find the dimension of del square del t square. Okay, so as you can see, what is the dimension of del t square? Okay, so this can be written as t to the power minus 2, because del t square can be written as 1 by t to the power 2. So this is the dimension. So uh, if I am taking this in the numerator from denominator, then what I will get? I will get a minus sign here. Okay, so I have got this. I hope this is clear to you. So now, as you can see, here is also magnetic field, in here is also the magnetic field, so the dimension can be cancelled out. Okay, so as you can see, if I am going to, okay, let me write it down here. So del square equals to mu naught epsilon naught del t square, only in terms of dimension. Okay, so what I can write? I can write that what is the dimension of del square? That means nebula square. That is L to the power minus 2. Okay, I am not writing the third bracket. Okay, keeping it simpler. So mu naught epsilon naught. This is the dimension of mu naught epsilon, and the dimension of 1 by t square is t to the power minus 2. Right. So what is the dimension of mu naught epsilon naught? This will be if I am going to take this t to the power minus 2 in the left side, to the left side, then what I will get? T square. Okay, right? I am going to get this t square L to the power minus 2, right? So if I am going to write it down here, okay, mu naught epsilon naught, I am going to get this. Okay, this is simple. Okay, what this was in the numerator, and I am getting it, writing it down here in the denominator. So what I am getting, I am just getting the minus x 1 minus sign. Okay, 1 minus sign. So L is here positive, t is here minus power 2, but here I am getting it positive. Okay, so if I am going to take this in the denominator, what will be happen? This will be got reversed. Okay, so what is this? I can write it down as, okay, uh, okay, let me write in the left side. Okay, so if mu naught epsilon naught have this dimension, then what will be the dimension of 1 by mu naught epsilon naught? Okay, then I will get one minus sign. Okay, L to the power 2 t to the power what? Minus 2. Again, what is this? L by t. Okay, I can write it down as this. Okay, so what is this? This is the dimension of velocity. So this is equals to velocity square, right? So I was just talking about this. Okay, so the dimension of 1 by mu naught epsilon is velocity square, is the dimension of velocity square, right? So I hope you got this. So what is this? What is the value of this? Okay, if I am going to put the value of 1 by mu naught epsilon naught, for mu naught and epsilon naught is for free space. By putting this value, the mu naught is the permeability of free space, and epsilon naught is the permittivity of the free space. Then what I am going to get? I am going to get this as 2.99 into 10 to the power 8 meter per second square. Okay, whole square. Okay, so this is, hope this is clear to you. This is the dimension of what? 1 by mu naught epsilon. This is what? This is velocity square. Okay, and this is the its value. I hope this is more clear to you. Now let me proceed further. So now what I am going to do, okay, let me add some space. Okay, okay. So now what was the equation? Electromagnetic wave equation. So let me add a line here. Okay, so what was the wave equation, right? The wave equation was del square E equals to mu naught epsilon naught del E del T, right? Okay, del square del E del T square, right? So now if I am going to find its solution, then what I will get? I will get the electric field as this. Okay, E equals to E naught, some magnitude term. E naught is the magnitude term, and e to the power I k dot r minus summation over I omega I t plus phi c. Okay, so what is E naught? E naught is the magnitude term, and it can be complex also. Okay, in some books, let's say the Griffith book, you will get this, it as E naught is written as like a this sign. Okay, so this represents that it can be complex also. Okay, this is the magnitude term. E naught is the magnitude term. And what is key? K. Okay, let me erase this. Okay, what is K? K is the wave factor. I hope you know that K is the wave factor. So let me write it down here. K is equals to wave factor. So what K represents? This K wave vector is simply the name of the term. Okay, right? But what is physical meaning? Okay, so let's say the wave is moving in direction. Okay, so if in this direction, if I consider a let's say unit factor, let's say k cap, so this is the factor so k is the factor which represents in which direction this wave is moving. Okay, so k is the wave factor, and it represents the direction in which the wave is moving. Okay, and r is simply position factor. I hope you all know that position factor can be written as x I cap plus y j cap plus z k cap, right? And okay, we don't need to solve this equation. Okay, this is much complex, but in this basic level you just need to remember the solution. Okay, so on solving this, what we will get a number of frequency terms. Okay, the wave not consist of simply one frequency, but it may consist of many more frequencies. Okay, so I hope you all have the concept of group velocity and phase velocity. Okay, so wave packet, so these have many frequencies. Okay, for simplicity, what I am going to take only one frequency term. Okay, that means I am going to take that the whole wave is consist only of one frequency. Okay, and the phi c, what is this is epo, that means initial phase. Okay, I hope we all know what is initial phase. Okay, and if there is only one frequency, then this is called monochromatic wave. So if I am going to consider monochromatic wave, then the summation sign will be removed. And if I am going to take that epo is zero, that means initial phase is zero, then what I am going to get, I am going to get the wave solution as this. Okay, so the electric field will be what? Okay, electric field will be E equals to E naught e to the power I k dot r minus omega t. Okay, so this summation sign is removed, since we have taken the monochromatic wave, and phi c is zero, since I have considered epo is zero. Epo means initial phase. Okay, so let's say now I am going to consider what? I am going to consider 1D wave. Okay, so uh, if initially I considered that this wave was moving in a random direction, let's say this is x y g direction, x y g. Okay, so let's say in the initial condition this was moving in a random direction, k cap, right? But now what I have considered, I have considered that the wave is moving in a fixed direction, let's say z direction. Okay, so if if the wave is moving in z direction, then what we will get that k dot r is the k dot r will be replaced by kz. Okay, so how this is happening? Okay, so let me write it down. Okay, so if the wave is moving in z direction, then what is k? I was talking that k is what? K is wave factor. So kx I cap plus ky j cap plus kz k cap, right? So this can be written as this, right? But if I am going to say that the wave is moving only in z direction, then what I can write? This two term will be zero, because if the wave is moving only in z direction, that means k cap direction, then we will have only this term, right? So what I can write? I can write this as what? k factor can be written as what? As k, okay, k z cap, or you can say k cap, right? So this is kz component. So let's say kz equals to k. For simplicity, I am writing it down as k kz cap, right? So you can take this k vector can be replaced by kz cap, right? Since the wave is moving only in z direction, x, and there is no dependency on there will be no component of x and y direction. Okay, again then r is what? X I cap, or let's say x cap plus y cap plus z cap, right? So on taking dot product k dot r, what we will get? We will get that on, since k have only the z component, so what we will get? We will get k z, right? So what I was writing here was this. Okay, so this is how k dot r is replaced by kz if the wave is moving in z direction. Okay, so if the wave is moving in one y direction, what we will get? We will get ky, right? And if the wave is moving in x direction, then what we will get? We will get kx, right? So I hope you have understand this. So this was the solution of electromagnetic wave equation in terms of what? Electric field. Okay, so on solving this equation, right, del square E equals to mu naught epsilon del square E del t square, we have got this solution. But what we will get if we are going to solve the equation? Okay, let me write it down. Solve the equation del square b equals to mu naught epsilon naught del square del t square of b. Okay, so what we will get? We will, obviously the solution will be in terms of magnetic field. Okay, so in terms of magnetic field, what we will get? We will get b equals to b naught e to the power I kz minus omega t. Okay, so this is the solution in terms of what? In terms of magnetic field. Okay, so what we have learned till now, we have learned that how to find the electromagnetic wave equation from Maxwell equation. So these are the two equation. One is this, and this is in terms of electric field, and the other is in terms of magnetic field, this one. And what was the next what was the next topic? Next topic was like to find the dimension of mu naught epsilon naught. Okay, so 1 by mu naught epsilon naught, it has dimension of velocity square, and what is its value? Its value is 2.99 into 10 to the power 8 meter per second whole square. Okay, so this is the value. Okay, and now what we have learned till this part, from this part, what we have learned? We have learned that what is the solution of these two equations. Okay, so one equation will give in terms of electric field, the equation which was in terms of electric field, this will give the solution as this. Okay, E equals to E naught. This E naught is in magnitude, and this can be complex also. Okay, and in terms of magnetic field, by solving this equation, okay, by solving this equation, what we will get? We will get this. Okay, on solving this equation. Okay, now I am okay. These are the two equation. Uh, okay, so what these two equation are is actually showing. Okay, these two equations are showing that how the electric field and magnetic field are varying. Okay, as the wave propagates in z direction. Okay. Now what I am going to, so I am going to find some, okay, let's say I am going to prove some properties of the electromagnetic wave from these two equations. Okay, so now let me proceed further. So I was considering what? I was considering a what? Monochromatic plane wave. Okay, so E can be written as E naught e to the power I k dot r. So k dot r is how we are getting this. I hope you all have understand. Let's say this the wave is moving in, let's say, in k cap direction. So the wave vector is k vector, and the r vector is simply an position vector. Okay, so now what we have got? Okay, so from Maxwell equation, what we have got? Del dot E equals to what? Rho by epsilon naught. Okay, see again in vacuum, that means in charge free space, what will be zero? Rho will be zero. Okay, since q equals to 0, so will be the rho will be 0. So again, what we have got, del dot e equals to 0. Okay, so now what I have written, del is replaced by ik. Okay, so how I am getting this, I will talk to you about it later. Okay, so is for this time you just consider it. Okay, del can be replaced by I dot k. Okay, so what is this? Del dot e will be replaced by I dot ik dot e. Okay, so I is just iota, the I equals to root over minus 1. Okay, so I can be 0, so k dot e will be 0. Okay, so what I can write, if k is not 0. Okay, since k in some direction the wave is moving, so k vector can be 0, and e naught, obviously e naught can be equals to 0. So what we will get, that k and e naught are what, perpendicular, right? Because if two factors if two factors are non-zero and their dot product is 0, then they are perpendicular. So now let me talk about this, how I was getting del can be replaced by ik dot. Okay, so now let me talk to you about this. Okay, okay, I'll need this, but now what I am going to do, so what is del dot e? Okay, so del dot e can be written as del x e vector I cap, obviously. Okay, and then what, plus del y e vector j cap, right? And then del z uh, e vector and then z cap, right? Obviously, uh, okay, okay, okay. So del dot e can be written as del x I cap e vector, right? Plus j cap del y e vector plus k cap del z e vector, right? Again, what was e? E was e naught e to the power I k dot r minus omega t. Okay, so what I can write, k dot r. Okay, what was k? K was kx I cap plus ky j cap plus kz k cap, and r was what, x I cap plus y j cap plus z k cap, right? So k dot r is simply kxx plus kyy plus kzz, right? Okay, okay. So what I can write, I can write it down as I cap. Okay, what, del x of e naught e to the power I kxx plus kyy plus kzz minus omega t, plus the differentiation in terms of y. Okay, so j cap del y and the same term, right? And similarly for k cap del z and the same term, right? So what I will get, if I differentiate this term in terms of what, in terms of x, with respect to x, then what I will get, differentiate on differentiating this in with respect to x, what I will get is I cap this is cap. Okay, okay, and then what I will get, this e naught e to the power I kxx plus kyy plus kzz minus omega t. Since this is in the power of e, so I will get this as similar. Okay, I will get the same term, and there will be an extra term, what, I k. This is iota. Okay, I k x. Okay, and for j I will get this same, and there will be an extra term I. Okay, only this term is same. Okay, and I will get ky, and for this is plus and plus k cap, what, okay, this term will be same, so I am not going to write it down, same term, and there will be an I k z. Okay, so now what I can write, this can be written as what, there is an I. Okay, if I just ignore this i's, okay, what I can write, okay, let me take here in the first. Okay, so if I take this x common, and what I will get, kx I cap plus ky z cap plus kz k cap. Okay, kx I cap plus ky z cap plus kz k cap, right? Okay, this is whole in the dot product with what, okay, this is what, this is e, right? So I can be, so it can be written down as e. Okay, and this is what, this is k vector, so I k dot e. Okay, so what I have got, I have got that del dot e is equals to I k dot e. So this is how I was writing that del dot e equals to I k dot e. I hope you all understand that how I am getting this. Okay, so let me move it here. Okay, so this was e, but I have written it down in the next line. What I have written, I have written it down as e naught. So how I have got this? Okay, so I am going to now talk about it here. So k dot e, right? So what is the direction vector? Okay, so k cap, actually, okay, some magnitude. Okay, some magnitude, k have some magnitude, let's say k, and k dot product is what, e vector have some magnitude, e naught. Okay, e naught have direction, and what is this term? Okay, this is dot product with what, e naught vector and e to the power I k dot r minus omega t, right? But this term is not giving us any what, not giving us any direction. Okay, so from which thing I am getting any direction, e naught. Okay, so what I can write, okay, e and this k and e to the power I k dot r minus omega t, this can be written as like this, and k cap dot e naught factor. Okay, so this is some magnitude, this, let's say this can be 0. Okay, it doesn't matter whether this is 0 or this is no, obviously the k can be 0 and this will be also not 0. So what we will get, we will get k cap dot e naught factor, okay, is 0. So this is how I was writing E as E naught. Okay, here E was replaced by E naught. Okay, here I have not written separated the K into into the magnitude and its direction. So let's say K have this. Okay, K cap into K. This can be together. So together this can be written as K vector. So this will be some magnitude. Okay, so this is how I have written E as E naught. Okay, so I hope you have understand this. So what we have got K and E naught are perpendicular. That means electric field and the direction of propagation are perpendicular to each other. So this is one of the property. Okay, so if the wave is moving, let's say in this direction, then what we will got electric field, the direction of electric field. Okay, let's say this is Z direction and this is X direction, then the electric field will be oscillating in perpendicular direction. Okay, so this is what this equation means. Okay, so this is electric field. Okay, okay. So why this electric field is looking like this? Okay, so this is the what, this is the maximum value of E, that means electric field. So this is E naught, and because of this exponential term, the magnitude of electric field will be at some point it will be decreasing, and at some point this will be increasing. So uh, from the starting point, the electric field, the magnitude of electric field will be increasing, then will then at this point this will reach a maximum value, and then it will be decreasing, and then again like this. Okay, so I hope you have understood. So similarly, I can write, what I can show that magnetic field and direction of propagation is perpendicular to each other. So let's now move to that point. Okay, similarly from Maxwell equation, what we have got that del dot B equals to 0. uh, Again from the same, okay, this is the proof. From this proof, okay, what I can write, I can replace this del as ik. Okay, so ik dot B naught, okay, equals to 0. So what if these are two factors and their dot product is 0, so they are perpendicular. Since what, since k is not 0, magnitude of k is not 0, and magnetic field, magnitude of magnetic field is not 0. Okay, so these two are what, perpendicular, right? Okay, so these two are perpendicular. So what I can write, hence magnetic field and direction of propagation is perpendicular to each other. Okay, so now what I am going to show, and now I am going to show that both electric field and magnetic field and the direction of propagation is perpendicular. So from this equation, what I can say, okay, if in this direction the electric field is moving, let's say this is Z direction, this is Y direction, so the magnetic field will be this, like this. Okay, so direction of propagation and direction of the magnetic field will be perpendicular to each other. Okay, so now what I am going to show, I am going to show that that E, B and Z, okay, that means K vector, both are perpendicular, okay, to each other. So to prove this, what I am going to take, I am going to take this Maxwell equation, del cross E equals to what, del T of B. Okay, so from the same argument, what I can show del cross E can be written as ik cross E. Okay, del can be written by ik. Okay, and then del T of B. Okay, what was the B? B equals to B naught e to the power I k dot r minus omega t. If I am going to differentiate this with respect to t, then what I will get, this. Okay, there will be an, okay, minus del T. Okay, uh, okay, B naught is constant, so it will be remain as this, and differentiation of this term will be, okay, I k dot r minus omega t. Again, differentiation of this will be what? Minus I omega, right? But there was an minus t term. Okay, so let me write it down here. Okay, so I minus minus got cancelled, so I omega, and this can be written as what? This can be written as b. So this is what I have written, I omega b, right? So now I got cancelled, and what I can write, k cross e equals to b, right? And if k can be written as what? Any factor can be written as its magnitude, and the product with its unit factor. Okay, unit directional factor. So k can be written as k into k cap cross e equals to omega b factor, right? So if k is the magnitude, so I can write it down here in the denominator in the right side. So k cap cross e equals to omega by k of b, right? So what I have got, uh, we all know that if there is a two factor, right? Let's say this is a factor and let's say this is b factor, and what we will get if we cross product this, let's say a cross b, then using right hand thumb rule, what we will get? We will get the direction of a cross b. So a cross b, so a cross b will in the direction of uh, in the direction perpendicular to the plane which contains a and b, right? So if, let's say, okay, let me make it clearer. So let's say in this plane a and b are here. Let's say this is a, this is b, so a cross b will be like this, so here. And what will be b cross a? B cross a will be in the direction perpendicular to this. Okay, so uh, if if a and b are in this plane, then the direction, then the a cross b or b cross a will be in the direction perpendicular to this plane. So if uh, k and e, here k cross e equals to, right, b. Okay, so if k and e are in this plane, let's say a is equals to, a is equals to k cap, and b is equals to what? B is equals to uh, e cap. Okay, this b is this factor, okay, not magnetic field. Okay, so then k cap cross e will be give the direction perpendicular to this plane, so magnetic field will be in this direction, right? This is the magnetic field, not this b factor. So k, e and b both are perpendicular to each other. Since k and e are also perpendicular to each other, direction of propagation and electric field is always perpendicular to each other. From the first, we have got this k and e are perpendicular. So what at the end, what we have got? We have got that the both e, b are perpendicular to the direction of propagation. So what we will get? Okay, what? Okay, uh, how now, how the wave will be look like? Okay, so I am going to draw that. Okay, so here I have written all those things as a summary. So, the three important properties of the electromagnetic wave are: electric field and direction of propagation is perpendicular to each other, magnetic field and direction of propagation is perpendicular to each other, e and then both eb and direction of propagation, and that is k, are perpendicular to each other. So now what I will write, so let's say this is what, this is the k direction, right? So in this direction the wave is propagating, this is k, right? So let's say the wave is moving in z direction, so k can be written as z cap. Okay, so now what I'm going to take, let's say this is x cap, and this is what, y cap. Okay, so now what we will get, since the wave is moving in this direction, so the electric field will be what, like, will look like this. The electric field must be what, must be perpendicular to what, perpendicular to the direction of propagation, right? So electric field is oscillating in this direction. Sorry. Okay. Okay. And how the magnetic field will look like? So again, electric field is perpendicular to what? Direction of propagation, that is say z, and magnetic field is also perpendicular to the direction of propagation. And again, from the third, what we have got, E and B are also perpendicular, right? So if electric field and B magnetic field are also perpendicular, so since E is in the x direction, it is oscillating in x direction. So what we can write, we can draw this as the magnetic field is oscillating in y direction, right? Okay. So this is the electric field. Electric field is oscillating in what? X direction, and magnetic field is oscillating in what? Oscillating in y direction. Okay. So this is not much clear. So let me insert a online photo here. Okay. So you will understand this. So this is what the electric field and magnetic field look like. Okay. So this is the direction of propagation. Here x is the direction of propagation, this is what x. Okay. And this is what, this is the electric field. Okay. So this is the electric field. Electric field is in y direction, this is the electric field. Okay. So the electric field is oscillating in x direction, the magnetic field is oscillating in z direction, this is z direction, and this is the magnetic field. And here the wave is propagating in x direction. Okay. So you can just replace it. This is I was explaining in this as I was explaining this as what, z direction. Okay. So this is what you can write. Okay. So this is all about today. Okay. So what we have learned today, we have learned today that the how to find the electromagnetic wave equation from Maxwell equation. One is this equation in terms of electric field, and the other one is in terms of magnetic field. One is this, and what is the dimension of mu naught epsilon naught, and that is the dimension of mu naught epsilon naught is the dimension of velocity square. And uh, how to now what we have learned after that, we have learned after that how to find the solution of electromagnetic wave equation. And from that wave equation, that means these and these, what we have learned three properties, important properties of electromagnetic wave. So what are those that the electric field and magnetic and the direction of propagation is perpendicular to each other, magnetic field and direction of propagation is perpendicular to each other, and electric field, magnetic field, and direction of propagation is perpendicular to each other. Okay. So and this is the your visual explanation. So this is the end of today's class. So thank you all, let's meet in the next class. Okay, thank you.